So, good day, guys. So, today we are going to be talking about molar heat capacity at constant volume and pressure. So, majorly in this video, we are going to be talking about three major things. The first thing is the relationship between molar heat capacity at constant volume and the change in internal energy, and we are going to be talking about the molar heat capacity at constant pressure, the relationship between the molar heat capacity at constant pressure and the change in enthalpy. So that's what we are going to be talking about today majorly. Okay, so good. So before we start talking about them one by one, let's first define some major things that we need to know here. First thing that we need to know is what is molar heat capacity. After that, we can define molar heat capacity at constant volume and pressure. Don't forget, the first thing, one of the things we are going to be learning from this video is get the relationship between CV and change in U and CP and what change in H. And apart from that, we will also be getting the relationship between CP and CV. When I say CV, I'm talking about molar heat capacity at constant volume, and when I say CP, I'm talking about molar heat capacity at constant pressure. And the last thing we are going to be talking about in this video is how to use molar heat capacity at constant pressure to get the change in H at different temperatures. So we are going to be talking about those three things majorly in this video. Okay, good. Now, like I said we need to know some definitions before we start checking them one by one. Now, when we say molar heat capacity, what do we mean? Actually, molar heat capacity is the amount of heat required to change the temperature of 1 mole of a substance by 1 Kelvin. Is the amount of heat required to change the temperature of 1 mole of a substance by 1 Kelvin. So if you are now relating it to constant volume, we are saying molar heat capacity is the quantity of heat required to change the temperature of 1 mole of a substance by 1 Kelvin at constant volume. Just add at constant volume to the definition, we get it right. And molar heat capacity at constant pressure too just means the amount of heat required to change the temperature of 1 mole of a substance by 1 Kelvin at constant pressure. That's what we mean by molar heat capacity at constant volume and molar heat capacity at constant pressure. Good. Now, take note, before we start checking out the relationship between things that we are going to be looking at, we should not forget that at constant volume, our QV, which is the quantity of heat required, is actually equal to our U. That's a constant. And at constant pressure too, our QP is actually equal to what? Is equal to H. So good. We are going to be talking about those things, so we should know those constants. Now, we defined molar heat capacity at constant volume, that's CP, to be equal to the amount of heat required. Okay, let's start from volume instead of starting from pressure. Good. So okay, our CV is actually equal to the change in QV over change in what? Temperature. That's molar heat capacity for what? For QV. And then we also defined this, okay, pressure. Good. We also defined CP to be actually equal to the QP over dt. Nice. So we are going to be solving this simultaneously, so we can easily get what we are actually looking at. Now, don't forget that at constant volume, this can be also be written as the change in U over dt. Why? Because at constant volume, our QV is equals to what? Is equals to U. We should not forget that. And these two can also be written as dH over what? Over dt. Did we get that point? Good. Now, so let's now take note that if I multiply all through by dt, I'm going to have my CV dt to be equal to the QV and is equal to what? Del U or du. And then here to I'll be having my CP dt to be equal to the QP and is equal to what? The H. So we should not forget that this P is just talking about constant what? Pressure, and this V2 is talking about constant what? Constant volume. Now, if I integrate both sides, if I integrate the CV dt is equals to the integral of the QV and is equals to the integral of what? The U. And this also be equal to the integral of d dt. Don't forget I'm integrating with respect to t at two different temperature. Good. Is equals to the integral of the QP and is equals to the integral of what? The H. So this is also at T2 and what? T1. So if I integrate this very well, what I'm going to be having is my CV open bracket, I will have T2 minus what? T1 is equals to, this will give me my QV and this will also give me my what? My change in U. Do we get? And this will also give me CP open bracket, my T2 minus T1, which is actually equal to my QP, which is equal to what? So this will give me my change in what? Change in H. So this is what I'm going to be having actually. But take note that majorly sometimes we can write our CV as a function of temperature. If we're writing CP as a function of temperature, can I see V as what? A plus BT plus CT square to move like that. The same way too, we can also write CP to be a function of temperature to be what? A plus BT plus CT square plus what anything we have. We can actually have DT cube and so on and so forth. Now take note that A, B and C, they are constant of a substance that are in view. They are constant of substance that are in view. That means this A, B and C varies with nature of substances. Do you understand? So take note. Now if I want to substitute this in this particular equation that I have, what am I going to have? If I'm going to substitute these two into this particular equation at the end, what am I going to have? So it's kind of very easy. Just substitute it and put it there. We are going to have the integral of T2 T1 open our bracket. We are going to have what? A plus BT plus CT square, good, plus CT square, and then we have dt, good. Dt is actually equal to our change in U, because I'm removing this, just changing U. And then we have what? There too, if I'm substituting this to this, I'm going to have the integral. This is T2 T1 open bracket A plus BT plus CT square. Don't forget we can have more and more, and what? Dt, everything to be equal to what? Our change in H. We should not forget that if I integrate this man here, the integral of this, I'm going to have change in H. And if I integrate these two here, what I'm having here too, I'm going to have what? Change in U. So you can see the relationship that I actually brought out from, we have CV and change in U, and then we can also write it in this form. If they give us our CV in terms of A, B and C as a function of temperature, the same thing we have here. If we have given CP in terms of A, B and C function of temperature, we can also write it in this form. So we have actually gotten a particular relationship between CV and change in U. We have gotten a relationship between CP and what? And change in H. We can see those relationships that we have there. So it's either they just give us if they give us a particular molar heat capacity at constant volume, and then they give us two temperature, we can actually use it to get our internal energy or change in internal energy. And if they also give us our molar heat capacity at constant pressure and two temperatures, we can actually use it to get our change in enthalpy. Good. So we have gotten CV, we have gotten CP. Now how can we get relationship between these two things? Okay, good. Let's check out how we can actually get that. The relationship between CV and CP, we can recall a particular formula, and the formula says we have H is equals to U plus PV, Kolrausch equation. Good. Okay, now looking at this here, let's now look at what we can do to actually get it in terms of CV and CP. Good. Now don't forget that if I integrate this, the H, if I add the and differentiate them in terms of temperature, that is over dt over dt over dt. Nice. Now del H over dt, if we go back to our notes, if we check out, go back to our notes where we actually have, okay, we have del H over dt, sorry, our del H over dt to be equals to what? Cp, right? So we can actually replace this, what we have here, to be what? Cp is equals to, now our del U over dt, let's check out, del U over dt is actually equal to what? Cv. So we can replace this here as what? As our Cv, plus now we have del PV over dt. Recall that PV for gases, PV is equal to what? nRT. That's our gas. If our n is equals to 1, certainly we are going to have PV to be equals to what? RT. So automatically I can replace this PV as what? As RT. That's what I'm having here, as RT. So we can actually have this to be equal to our CP is equals to CV plus the RT over what? Over dt. Now don't forget that R is constant, so I can bring R out. So we have CP is equals to what? CV plus R dt over what? Over dt. So this dt can cancel out this dt. So we can now CP is equals to what? CV plus what? Plus R. So automatically I can actually say, okay, my CP minus CV is actually equal to what? Is actually equal to R. So this is the relationship between CP and what? And CV from Kolrausch equation. Do we get? Okay, good. So we have gotten that to be that. So let's now check out. We got equation that's connecting CV and del U. We also get an equation that is actually connecting CP and del H. But all these are just looking at when we just have just the change in enthalpy of a particular system. What about if we have from reactant to product? Can we use our this particular formula we just derived to also get the change in enthalpy at different temperature? And if we can actually use it, how can we use them? Let's check out how we actually derive it, so we can actually get the major view of what we are talking about. A going to reactant B, so going to product B. So how do we now get the change in H or the change in U at different temperature when we are talking about a particular reaction that is moving from A to B? Okay, so let's check out. Now with this, we can see our change in U of A moving to B is actually equal to our UA minus UB. Or sorry, this will be UB minus UA. Good. This should be UB minus what? UA, because it is product minus what? Reactant. Okay, good. So with this, if I want to differentiate this in terms of temperature, then I'm going to have my D change in UA minus to B is actually over the T. Good. Is actually equal to the UB over the T minus the UA over what? Over the T. Nice. Okay, good. Now this is going to give me the change in UA to B to actually be equal to the T to be equal to, now what I'm actually having here is actually equal to what? My CV for B minus my CV for what? For A. And how do I know that? Now don't forget that our change in U, the U over the T is actually equal to what? To CV. Anytime we have CV over the T is actually equal to this. So we should not forget. Good. Okay, so let's move on. Good. So with this now, this is actually equal to our change in what? Change in CV. Good, because we are moving from A to what? To B. So I can then rewrite this as the change in U from A to B over the T to be equal to the change in what? CV. If I cross multiply, I'm going to have the change in U when we move from A to B to be equal to change in CV dt. Good. Now they give us at different temperatures that we should actually get the difference in the change in the change in internal energy for both. I can easily integrate. So if I integrate this in terms of temperature T1 and T2, I have the change in A to B, good, to be equal to, this will be the integral of what? Change in CV dt. Good. Okay, so let's move further. Let's check it out. So if I should integrate this, the integral of this is telling me that okay, I should actually get the change in internal energy for B and then minus it in change in internal energy for A in at when we are moving from A to B at different temperature. So eventually what this is telling is that okay, we are going to have the change in U2 minus change in U1. This is my change in internal energy for temperature 2, and this is my change in internal energy for temperature what? Temperature 1. Do you understand? And it's okay, everything will actually be equal to the integral. Good. Oh, sorry. Let me input this very well so we can help. So okay, good, nice. So we know that we have, for this we are going to have change in U2 and change in U1. These are for temperature 2 and temperature 1 to be equal to the definite integral of T2 T1. We have change in CV dt. Good, this should be dt, please. Good, dt. Nice. Okay, so what do we now do after this? So we should not forget that okay, our CV can be written as the in terms of temperature. So it will be what? A plus BT plus CT square and so on and so forth plus 1. So this thing means we can actually have DT cube and so on and so forth. But to avoid complexity, we can just stop at CT square plus so on and so forth. So this is what CV is. But what we have here is change in CV. So we can still confirm that okay, our change in CV to be equal to our change in A plus the change in BT plus the change in CT square and so on and so forth. Please take note that the number of moles are taken into considerations whenever we start solving for this. So we can actually put our n at the outer part, but it's not actually necessary. But we should take note that when we are solving for A, we will take into consideration the numbers of moles. When we start solving questions on them one by one, we tend to know what they actually means. So we can actually write okay, this is changing U2 minus change in U1 to be equal to, we have the integral of T2 T1, and we have change in A plus change in BT plus change in CT square and so on and so forth. So good. So we should not forget, if I integrate this the way it is, don't forget we have dt in terms of t. So we are going to have change in U2 plus change in U1 is equals to, this should give me my change in AT, good, change in AT, plus this will be change in B over 2T square. We should not forget this is a to the power 1. We have 1 plus 1 divided by 1 plus 1, which is 2, plus the next thing I'm going to have here, good, is changing C over 3. We have T cube plus so on and so forth, and then what I'm going to have here to be what, T2 and what, and T1. So if I should move further, here, I'm going to have my change in U2 minus change in U1 to be equal to, open your bracket, we have change in A, we have T2 minus what, T1, and we have plus change in B over, we have what, over 2, we have T square 2 minus T square 1, good, plus the next one will be changing C over what, 3, we have T cube 2 minus what, T cube 1, very good. If we have further to, we can actually replace this as this. You can see that at different temperature, where we can actually get our, if this is a particular internal energy at a particular temperature T2, and this is the internal energy at a particular temperature T1. And since if we are given these terms and we are given one of these, you can easily look for the other one. And even though they didn't give us any of these, you can actually get the change, the difference between them, and then use these parameters to get them. Do you understand? And then one particular thing that we have to take note is that we can also replace this in terms of H. We can see the way we actually did it for we use CV here. We can actually use CP2 using the same procedure, and at the end of the day, what we are going to be having is our change in H2 minus change in H1 to also be equal to, open your bracket, we have change in A, open bracket, T square minus T1, good, plus we have change in B over 2, open bracket, we have T square 2 minus T square 1, good, plus we have change in C over 3, and we have T cube 2 minus T cube 1. Nice. So we can actually use this particular formula to also get the enthalpy at different temperature. So you can see that with this formula, with this kolrausch formula, we can actually get the enthalpy not at only standard temperature but at different temperatures, so apart from the standard temperature. So if they give us the enthalpy at standard temperature, and they also ask us to look for the enthalpy at other temperatures, we can actually apply this formula once this A and this B are given. Now don't forget that A and B and C are constant of the substance that are involved, the substance that are in view. And this change in A is just talking about, okay, if we have product and reactant, we have to add all the A's for product and all the A's for reactant and get the difference between them. That's product minus reactant. That is what will give us for this A. And the same thing to applies for B and C. The change, we are adding up everything we have in product, adding up everything we have in reactant, and get the two differences. That is what we are talking about when we talk about change in A, change in B, and change in C, so that we can have the major view of what we are talking about. Let's take one example. Good. Okay, so now let's look at this question. This question is giving us a particular formula, CO plus O2 to give us CO2, and then they ask us to get the change in H at 47 degrees Celsius, whereby giving us our standard enthalpy. When we say standard enthalpy, we are talking about a temperature of 298. That's the standard temperature. So they give us the enthalpy at standard temperature, and they ask us to look for the enthalpy of this using the molar heat capacities of everything they give us. Now, what do we have to do? So we can easily recall the formula. Okay, we said there's a formula that says change in H2 minus change in H1 is actually equal to change in A open bracket, we have T2 minus what T1 plus change in B over 2 open bracket, we have T squared 2 minus T squared 1, good, plus we have change in C over 3 open bracket T cube 2 minus what T cube 1. So you can easily recall this formula. We are stopping at C because what they give us is just A, B and what C. You can see how they will give us A. So how do we get change in A? We say, okay, to get change in A, we are going to add up the reactant, add up the product, and then get the difference between them. So that will be very, very easy. So our change in A is just the reactants that we have. The reactant is CO and O2, right? This is for CO and this for O2, right? Very good. And then the product is just this. So to get change in area to be 26.78 minus, now the addition of the reactant, we have CO to be 26.53 plus, now the one for O2 is 25, right? But we have to take into consideration the number of mole. So how many number of moles of O2 do we have? Is 2, so we have to divide it by half. Is 1 over 2, so we have to divide this by half. So at the end of the day, so this change in A, so our change in A will actually be equal to, let's tap our calculator to see what we are going to get as our final answer. 26.78 minus the addition of 26.53 plus we have 25.52 divided by 2, good, divided by 2. So we are having minus 12.51 as our answer, minus 12.51, good, as our change in A. So change in B to the same way. We are going to add up the reactant, add up the product, and then see what we are going to have. So for B, what we have as our product is just this, so we have 42.26 minus, so for the reactant, what we are having as the reactant is CO and O2. So sorry, there is a slight mistake here. So let's get this. So this should be to multiply 10 raised to power minus 3, good, minus, we have open bracket, good. So what we are having as our CO, for CO alone is 7.7 times 10 raised to power minus 3. So we are adding it with the one for oxygen. Oxygen is what, 13.6 times 10 raised to power minus 3. We have to take into consideration the number of moles, so we have to divide it by 2. So what we are going to have for change in B is, we have 42.26 to minus the open bracket, we have 7.7 to add up 13.6 divided by 2. So what we have here is actually 27.76, then to multiply 10 raised to power minus 3. You can see what I just did here is take their first numbers. Reasons is because the 10 raised to power minus 3 is actually similar to everything, so I can just substitute that out and then work with what we have at the front. So to get our change in C2 is kind of very, very easy. It's the same way too we did that. Our value for CO2 is what, minus 14.23 to multiply 10 raised to power minus 6 minus, we open our bracket, what we have as our normal CO is what, minus 1.17 times 10 raised to power minus 6 to add what we have as O is what, 4.27 times 10 raised to power minus 6, then we have to divide it by what, by 2. So since minus 6 and 10 raised to power minus 6 is similar to everything, you can just take what we have at this front, that is minus 14.23 to minus what we have, what, minus 1.17. so don't forget we are having a minus sign here, so here should be minus, so it will be minus 4.27 divided by 2. So we're having 4.27. Then we divide this by 2. Good. Then we close our bracket. So what we are going to have as our final answer is actually minus 10.925. Good. Times 10 raised by what? Minus 6. So we have gotten change in A, change in B, change in C. And don't forget that our T2 is the final temperature, which is 473. Our T1 was our T1, that's the standard temperature, which is what? 298. Now to get our change in H1, change in H1 is also the heat content of the product minus the heat content of the reactant. The heat content of the product at standard temperature that they give us here is what? Is minus 392.5. So we minus it from what? The heat content of the reactant. This is content of the product, CO2. For the reactant here is what? Minus what? Minus 110.5. Good. So our change in H1 will be equal to minus 392.5 plus 110.5. And that should give us change in H1 to be equal to, we can tap our calculator, minus 392.5 plus 110.5. So automatically give us what? Minus 282 kilojoules. Now don't forget that this is included. So we have gotten automatically everything we need to get our H2. Because we have gotten H1, we're going to change in it. We know our T2 and T1. Now, so we will just substitute this, each of them in the equation, and then once we substitute, then we can now solve one by one. So let's check them. Let's check out how we substitute them and get our answer very fast. So good. Okay. So we have, don't forget that our change in H1 that we got, change in H1 is what? Minus 282 kilojoules. Our change in A, that we got, A is minus 12.51. And don't forget our change in B. The change in B that we got is actually 27.76 times 10 raised per minus 3. And our change in C, is what? Minus 10.925 times 10 raised per what? Minus 6. So that's what we got for that. And we know our T2 is what? Our T2 is actually 473, and our T1 is actually what? 298. So we can then recall the formula that says, okay, change in H2 minus change in H1 is actually equal to change in A, open bracket, we have T2 minus T1 plus change in B over 2, we have T squared 2 minus T1 square, plus we have change in C over 3, open bracket, T cube 2 minus T cube 1. So we can then start substituting. We have change in H2 minus the one that we have here for change in H1 is what? 282. Don't forget this is in kilojoules, is equals to our A is what? Minus 12.51, open your bracket, we have 473 minus 298, 473 minus 298 plus, okay, this will be minus, okay, this is actually plus 27.76 times 10 raised per minus 3 divided by 2, and then we have our T2 to be what? 473 square minus 298 square, good, plus our change in C, this should be negative, it's going to be negative 10.925 times 10 raised per minus 6, and then we open our bracket, we are going to have here is 473 cube minus 298 cube. So we can then press calculator very fast. 10 raised to minus 282 kilojoules is actually equal to, so if I do this fast, I'm going to have minus 12.51 minus 12.51 2.51 to multiply, or just open bracket, get them one by one. So we're having 12.51 to multiply, or just open your bracket, 473 minus 298, close your bracket. So what we are having there is actually 218. We're having 2189.25. Good. Plus, now the next thing, don't forget we have minus, so there should be negative at the front. Good. And then the next one is we have 27.76 to multiply 10 raised to power minus 3. Good. Don't forget we are dividing it by 2. Then we open your bracket, we have 473 square minus 298 square. You can just easily press calculator to get our answer. So what we have here is 1872.759. Good. So minus, the next thing we are having is we have 10.92 times 10 raised to power of minus 6. Don't forget we are dividing it by 3. Good. So divided by 3, then open your bracket, we have 473 raised to power of 3, then minus we have 298 also raised to power of what, 3. So good, also raised to power of 3. Then remember to close our bracket. Good. So what we have here is actually minus 288.871. So good. So this is what we are just having here. And but don't forget that this is actually in what, in joules. So we have change in H2 minus 282 kilojoules is equal to, so we have minus, good, we have minus 2189.25 plus 1872.759 minus 288 we have 871. Good. So what we are having at is actually minus 605.362 joules. Now normally to get our H2 is just equal to minus 282 kilojoules. No, when we actually bring it here, this will be plus, and this should be minus 605 point what, 0.362. So this is what we are actually having here. Good. Okay. So so there is something we should take note. I think this is actually having a minus sign before. This is actually having a minus sign. So, and what we have here is minus. So if I'm inputting this minus here, minus, you can actually counterbalance this minus. So it will actually change this particular minus here to what? To positive. Since we are bringing it and there's the minus sign here, so to be positive, this will be positive, this will be positive. So if I'm bringing it to this other side here, good. If I'm bringing to this other side, automatically this will be what? Will be negative. So we're having this to be what? To be in joules. So we have change in H2 to be equal to minus, we have 282 minus 282, and we have minus what? Since this is in joules, we can change it to kilojoules, so we can add them up. So we divide this by 1000 to give us 0.605 kilojoules, and this is already also in what? In kilojoules. So adding the two of them up, we have our change in H2 to be actually equal to, we have minus 282.605 kilojoules. So this is our answer for H2. You can see that with the formula we can actually get the change in enthalpy, not for only standard temperature, at other different temperature too. So eventually we have gotten our H2 to be equals to minus 282.6 kilojoules. So please subscribe to my YouTube channel remain a light tutorial. Thank you.